In this lecture video, we are going to talk about heat. As we learned in the prior topic, heat is the change in thermal energy due to a difference in temperature. So in mechanical energy, we talked about work being the change in mechanical energy. Here we're going to talk about heat being a change in thermal energy. So you have to think about work and heat conceptually the same way. We are going to use the symbol Q to represent heat. And because it is a change in energy, the units once again are going to be joules. And in fact, this chapter and next chapter, joules are going to be the unit a lot because we're going to be talking a lot about conservation of energy again. In order to be able to calculate the change in thermal energy or the heat, we need to discuss something called specific heat. Now we have to be careful here. The word heat is in the name, but it's not the same thing as Q. There are going to be more terms that are part of the specific heat than just heat. Specific heat is defined as the energy required to raise 1 kilogram of a substance 1 degree Celsius. So this is a value that is going to depend upon the substance you're talking about. And the higher the specific heat, the more energy you need to raise the same amount of material, the same temperature, as you do something with a lower specific heat. And the example I always use for this is going to the beach in the off-season. When you go to the beach in the off-season, the ocean is still cold, but the sand is hot. And the reason is the difference between the specific heat of the ocean compared to the sand. Water has a very high specific heat. Sand, the materials that make up sand, have a lower specific heat. So even though it's under the same sun for the same amount of time, it needs more energy to heat up the water than it does the sand, which is why you get that temperature difference. Now that we have discussed specific heat, we can learn how to calculate heat, or that change in thermal energy due to a difference in temperature. We're going to say heat is equal to mass. So this is mass in kilograms times specific heat. So we're going to use a lowercase c to stand for specific heat. And this is going to be in joules per kilogram degrees Celsius. And then we're going to multiply that by temperature final minus temperature initial, so the change in temperature. And because you're subtracting, you can either be in degrees Celsius or Kelvin, as long as both are in the same units. And we can then use this to find the total energy change for a system. Where you would take the change in thermal energy for one object in the system plus the change in thermal energy for another object in the system, and if there's a third object, you'd add another change in thermal energy. And you would sum them together in order to find the total energy change. And this is very similar to the concept of when we were dealing with work, we added together work non-conservative plus work conservative to find the total work done. So we're just splitting it up based upon the substance because the specific heat of each substance is going to be different. Now sometimes we may use a different relationship to represent the amount of material that we have. In physics we tend to use mass, but in chemistry you tend to talk about number of moles. So lowercase n in this relationship is the number of moles. And moles is, I always consider it a counting unit, where in order to have a mole of something, you need 6.02 times 23 of that particular substance, so Avogadro's number's worth. So in order to have a mole of oxygen molecules, you need to have 6.02 times 10 to the 23 of them. And to get from the mass of the substance to the number of moles, we need to use this relationship here, where this new variable down here, my capital M with some feet on the bottom of it, is going to be the molar mass. And typically you're given the molar mass in a periodic table, so carbon, for example, has 12.01 written underneath of it. So that would be the molar mass, but you do have to be careful because the molar mass is given in grams per mole. But in physics we never use grams, we use kilograms. So you need to convert to kilograms per mole before doing any calculations. So you need to divide by 1,000 before you use the number given in the periodic table. This here then is going to be the molar specific heat, which is going to have units then of joules per mole Kelvin rather than joules per kilogram Kelvin or kilogram degrees Celsius. The Celsius or Kelvin actually doesn't matter in this particular constant. And we'll talk more about molar specific heats as we progress through this particular unit, so they are going to pop up occasionally.